Welcome back to AI.Code.Cast. Today, we're diving deep into a classic coding problem.
Hmm.
The one they love to throw at you in interviews. It's called best time to buy and sell stock.
Ah, yes, a real classic. And a great one for demonstrating some really fundamental algorithmic concepts.
So imagine you're given like this list, right?
Hmm.
This array that represents stock prices over a certain time period.
Right.
And the goal is to figure out the best day to buy and the best day to sell so you can maximize that profit.
Exactly. But there's a catch. You can only buy once and sell once.
So no going back in time to snag that super low price after you've already sold.
No time travel allowed, unfortunately.
Right. So if we were only looking at a few days of stock prices, we could probably just, look at it and figure out the best times to buy and sell. But what if we're dealing with years worth of data?
Hundreds, thousands of price points.
Exactly. That's when things get a little more challenging.
It definitely gets more complex computationally.
So what would be like the first approach that comes to mind? I mean, it seems like we could just compare every single buying day with every single selling day and see what gives us the most profit.
That's the brute force approach, just systematically checking every single possibility.
Okay, but with a massive amount of data, that sounds like it could take forever.
It would take a really long time. You're essentially trying every key on a giant key ring to see which one unlocks the door. It'll work eventually, but it's not very efficient.
So let's say we have like 1,000 days worth of stock prices. Checking every single pair of days would be, well, a lot.
Exactly. The time complexity for this brute force method would be O of n squared, where n represents the number of days. So as the number of days increases, the time it takes to run this just explodes.
So not really a good solution for, massive amounts of data.
Not really scalable.
So we need a smarter approach then. Something that can handle these massive data sets without taking forever. But before we jump into that, what if there are multiple days with the same lowest price? Does it matter which one we choose to buy on?
That's a great question. And the short answer is no, it doesn't. Because our main objective is to maximize profit, right?
Yeah.
The specific day we buy doesn't actually impact the profit as long as we're buying at that lowest price.
Right. It's all about selling at the highest price later on.
Exactly.
So we're basically looking for the lowest valley and then the highest peak in our stock price chart. Kind of like we're, hiking through a mountain range trying to find the best buying and selling spots.
I like that analogy. It helps to visualize what we're trying to achieve. So then the question becomes, how do we find those valleys and peaks efficiently without resorting to that brute force method?
Right. So instead of checking every combination, what if we just went through the list of prices once?
Just one pass through the data.
Yes.
Now you're thinking.
But how would we keep track of the best buying and selling points as we go without looking back?
Here's the clever part. As we move through the list, we can keep track of two key things: the minimum buying price we've seen so far, and then the maximum profit we could make based on that minimum.
So we're basically assuming the best time to buy is always the lowest price we've seen up to that point.
Well, we're not trying to predict the future. We're making decisions based on the information we have at each point in time.
Okay, I see. So we're constantly updating our minimum buying price as we move through the array.
Exactly. And for each day, we calculate the potential profit if we were to sell on that day.
So we're saying, okay, if I had bought at the lowest price I've seen so far, how much profit could I make if I sold today?
And we just keep track of the highest potential profit we've come across. It's a type of algorithm called a greedy algorithm, where we make the best decision at each step without looking back.
So if we see a price lower than our current minimum buy price, we update our minimum. And for each price, we calculate the potential profit and update our maximum profit if it's higher.
You got it. It's all about finding the best entry point, the lowest valley, and aiming for the highest peak, the best exit point.
This sounds so much more efficient than that brute force method we talked about earlier.
It is. The time complexity for this one-pass approach is O(n). It scales linearly with the number of days, which is a huge improvement.
So instead of comparing every single pair of days, we only have to go through the data once. That's amazing.
And we're making these smart, greedy decisions at each step without having to look ahead or backtrack.
This one-pass method is really impressive. But are there any other things we should be thinking about? Potential problems or limits to this approach?
That's a great question, and it leads us to another fascinating approach for solving this problem. But before we get into that,
All right, let's hear about this other approach. What other tricks do we have up our sleeve?
Well, let's talk about the two-pointer approach. It's a different way to think about solving this problem, especially when we're limited to buying and selling the stock only once.
2 pointers, huh? Okay, I'm listening. What exactly are we pointing at?
So imagine we have these two pointers. One we'll call left and one we'll call right. They're moving across our array of stock prices. The left pointer is going to represent the day we buy the stock, and the right one, that's the day we sell.
Okay, I'm picturing it. Like two little scouts exploring our stock price mountain range.
Exactly. So how do these scouts work together? Well, we're going to move these pointers strategically to check out different combinations of buying and selling. We'll start with the left pointer at the very beginning of our array, and the right pointer, that'll be just one step ahead.
So, like, we're thinking about buying on the first day and then selling on the second day.
You got it. And as we move these pointers, we'll keep track of the maximum profit we've seen so far. Now here's the key. We have these rules for moving the pointers.
Okay, what are the rules? How do we know when to move left, right, or both?
All right, so rule number one. If the price at the left pointer is less than the price at the right pointer, that means we could potentially make a profit. So we calculate that profit and compare it with the maximum profit we've stored. If it's higher, we update our maximum profit. Now, regardless of whether we update that maximum profit or not, we're always going to move that right pointer one step forward.
So we're kind of saying, all right, if I bought it left and sold it right, would I make more money than my current best profit? And then we check the next day to see if selling then would be even better.
That's exactly right. Now, what if the price at the left pointer is greater than or equal to the price at the right pointer?
Well, in that case, it wouldn't make sense to buy at the left and sell at the right, right?
Yeah.
Because we wouldn't make any money. So would we move both pointers forward then?
Not quite. In this case, we're going to move the left pointer to the current position of the right pointer. The idea is that this new left position might give us a better opportunity to buy low.
Ah, I get it. Like we're saying, this left spot isn't great. Let's try shifting it to the right and see if we can find a better deal.
Precisely. We're always on the lookout for those lower buying prices, those valleys in our mountain range. And the right pointer, it keeps moving, exploring those peaks, searching for the best time to sell.
It's like a little dance between these 2 pointers, one seeking valleys, the other hunting for peaks. But is this method as efficient as that one-pass approach we discussed?
You bet it is. The time complexity of this two-pointer approach is also O(n). We're basically doing a single pass through the array, even if our pointers are moving back and forth a little bit.
Wow, so we still have that linear time complexity, which is awesome. It seems like we've got another really powerful tool for solving this stock problem.
We do. And what's really cool is that this two-pointer approach is kind of similar to other techniques we use for solving problems. Have you ever heard of the sliding window technique?
The name rings a bell. Isn't that where you have this window that slides across the array?
That's exactly it. And you know what? This two-pointer approach can actually be seen as a specific type of sliding window technique. The left and right pointers, they define the edges of our window, and as we move them, we're sliding that window, checking out different buying and selling possibilities within that window.
So it's not just 2 pointers moving around. It's this deeper concept that connects to all sorts of other problem-solving strategies.
Absolutely. That's what makes these algorithm problems so fun to explore. You start seeing these hidden connections, like these different approaches actually share some common ground.
I'm really enjoying how all these elegant solutions are coming together. We've gone from that brute force approach to these much more clever strategies. But before we get too carried away, is there anything else we need to think about with this 2 pointer approach? Any downsides or limitations?
That's a great question. The two-pointer approach is really good when we're only allowed to buy and sell the stock once, but there's a catch. Well, the two-pointer approach works great when we're limited to a single buy and sell transaction, but it kind of falls apart when we can make multiple trades.
So our trusty 2 pointer method is great for finding that one perfect trade, but it can't really handle the complexities of, like, a multi-transaction strategy.
Exactly. If we could buy and sell multiple times, we'd need a way to handle a whole series of trades, riding those peaks and valleys in the stock prices.
Right, like we're not just hiking through the mountains once. We're trying to become expert day traders, making the most of every up and down.
I like that analogy. So how would we approach this more dynamic scenario where we're allowed to make multiple trades?
Well, our one-pass and 2 pointer methods are great for finding those single best trades, but they don't seem equipped to handle a sequence of trades. Do we need to bring in, like, a whole new set of tools for this?
We might need something a bit more powerful. One technique that often comes up for this type of problem is dynamic programming.
Dynamic programming. That's a name that always sounds kind of intimidating. I've heard it described as a divide and conquer strategy.
Yeah, that's a good way to think about it. Dynamic programming is all about breaking down a big, complex problem into smaller, more manageable pieces. And then we solve those smaller problems and store the solutions so we don't have to redo the same calculations over and over again.
So for our stock trading problem, we could use dynamic programming to keep track of the maximum profit we could make at each day, considering all the different things we could do: buy, sell, or just hold on to the stock.
Exactly. It's about making those smart decisions at each step, knowing that our choices today can affect how much profit we make in the future.
Sounds like a pretty intricate approach.
Hmm.
And I imagine it could get pretty computationally heavy, especially if we're dealing with a lot of days and potential trades.
Yeah, you're right. Dynamic programming can be quite computationally intensive, especially when you have a lot of data. But it's often the best way to handle problems where you need to make a series of decisions. And those decisions depend on the choices you made before.
Well, it seems like we've just scratched the surface of another fascinating topic here. Dynamic programming definitely deserves its own deep dive. But for today, I think we've covered a lot of ground. We started with that simple brute force approach, then explored those elegant one-pass and two-pointer methods. And now we've even glimpsed into the world of multi-transaction strategies and dynamic programming.
It's been a great journey through the best time to buy and sell stock problem. We've not only learned about specific algorithms, but also seen how different approaches connect and gained insights into broader problem-solving strategies.
We've seen how algorithmic thinking can help us tackle real-world problems, even those involving the complexities of the financial market.
So until next time, keep those coding skills sharp, and remember, whether you're navigating a mountain range of stock prices or any other algorithmic challenge, the joy is in the journey of exploration and discovery.
Happy coding, everyone!